In response to question A1, the first place you could solve this using the idea of rho gy. That's a formula. Don't want to use that. And I'll say not yet, but soon. I mean, like very soon, before the end of this class. Okay, now, more pressure in the bottom. Well, you have a rectangular region, rectangular object in water with the bottom and the top in horizontal planes. There's more pressure on the bottom than there is on the top because the bottom is deeper than the top. Now, the pressures on the sides equal out. They balance each other. They exert no net force on the object, but the greater pressure on the bottom exerts more upward force than the pressure on the top exerts in the downward direction, giving you a net upward force. And that force is going to be our buoyant force. Okay, so more pressure on the bottom, more force on the bottom than on the top. Now, to get the idea, we got water here. We'll let this be our object. And we think of a column of water here down to the level of the top of the container. The water in that column, just whatever column of any uniform cross-section, a cylinder, a prism of uniform cross-section, the water in that column has to be supported by some force because it has weight. And the force exerted at the bottom comes due to the pressure, the upward force of pressure on that column of water. And we worked that out earlier. We saw how that works, and we can use this model to get the pressure here. We can use the same model to get the pressure here, except that I didn't tell you how deep this thing is. The reason I didn't tell you how deep it is because water's incompressible, at least for the purposes of this course right now, so that it doesn't matter how deep. All that matters is what the difference is between this pressure and this pressure. And if you think about it, that difference has to be equal to the difference of, equal to the pressure you would get by analyzing this column. Okay, this column being the difference between this column and this column. Okay, in other words, the column that extends from the point A at the top to point B at the bottom. So the change in pressure between A and B is equal to the pressure needed to support just this column. And we can work that out by the same methods we've used previously. And we find that since the bottom is 2 centimeters deeper, we have a pressure difference of 200 newtons per square meter. Now that would be following the same procedures we used previously. And actually I just did this by proportion. We found in the last class that a 2 meter depth would correspond to pressure difference of 20,000 newtons per square meter. 2 centimeters is 1/100th of that, so this is 1/100th of that 20,000 newtons per square meter. Now the area of the top or the bottom is 15 square centimeters or 0.0015 square meters. It follows with just a little bit of calculation, multiplying this by the pressure difference, that the difference in the forces on the bottom and on top is 0.0015 meters squared times 200 newtons per square meter, or 0.3 newtons. Now the next question, if this 30 cubic centimeter area or volume was filled with water, what would its mass be? And what would its weight be? Well, that's very straightforward. 30 cubic centimeters has mass 30 grams, 0.03 kilograms. Its weight is then 0.3 newtons, and this is the same as this. Okay? Well, this is the difference in the forces exerted from below and the forces exerted from above. That's your buoyant force. This is the weight of the water that would fill this container, and that is then the weight of the water that this container displaces when it's submerged to whatever point. And now we have Archimedes' principle. The buoyant force is equal to the weight of the displaced water. Now that proves it. It doesn't prove it, but if you did this symbolically, you'd have a proof for rectangular objects. To go beyond rectangular objects, you're going to have to do surface integrals and think about normal directions and the component of the normal direction and the vertical direction and stuff like that. If you've had multivariable calculus, you know what I'm talking about. It's not impossible to do that depending on the container. If you can express the shape of the container easily, you can actually set up the integral. Otherwise, you use that idea to prove that it's going to be that way for any container.